following this one, we'll be studying probability. And in the study of probability, counting possibilities in certain situations is very important. So in this section, we're going to talk about counting principles. Consider this problem. Suppose we flip a coin, and then following that, we roll a six-sided die. And we'd like to know all of the possible outcomes in performing these two tasks back to back. Well, the safest thing to do in counting the possible outcomes in a situation like this is to list them all and simply count them. So now when we flip a coin, we know that there are two possibilities. We can either get a head or a tail. And when we roll this six-sided die, we can get either a 1 or 2 or 3 or 4 or 5 or a 6. So one outcome is flipping a head and then rolling a 1. Another outcome is a head with a 2, head with a 3, head with a 4, head with a 5, head with a 6. And then we have to go through all of those possibilities if we flipped a tail on the flip of the coin. So the tail could be associated with 1, T2, T3, T4, T5, T6. And then, after listing all of the possibilities, we just count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 possible outcomes. But a technique that can be utilized in this problem and in other problems where the counting is extremely inconvenient, if not impossible, if the number of outcomes is extremely large, is to do this. Just decide how many possibilities there are for the first situation, for the first event here of flipping the coin. Well, there are two possibilities, a head or a tail. And for rolling the die, it's 6 possibilities. And you simply multiply the possibilities. That is, we have 2 possible outcomes for the flip of the coin. We multiply times the 6 possible outcomes for rolling the die. 2 times 6 gives us the 12 total possible outcomes. Here's another situation. Suppose we want to determine the number of 2-letter words that are possible. Now we're using letters of the alphabet, and we'll just say that any 2-letter combination forms a word. All right? Even if it's AB, that's a word. Okay. Now how many are possible? Well, in a situation like this, the question will come up. Well, let's see, if we're multiplying our possibilities here, then we know that there are 26 letters in the alphabet. So when we choose the first letter for our first word, or when we determine the number of choices for the first letter, we're saying it's 26. Now the question becomes, do we include in the list of choices for the second letter the letter that we chose first? That is, if it's kind of like this. We can set it up almost like an experiment where we have the letters of the alphabet written on little slips of paper, and we throw those little slips of paper into a hat, and we shuffle them around, and someone draws a letter. Okay, so the letter is drawn, and there were 26 possibilities before the letter was drawn. Now, once that letter is read and recorded, what do? Do we take that letter that we had drawn out to begin with and put it back into the hat for the second drawing, or do we leave it out? Now that's called with or without replacement, and it makes a big difference in the outcome of the situation. That is, how many possibilities there are. Without replacement, that is, without including the first letter in our choices for the second one, it would look like this. Now remember, we're just multiplying the choices here. The number of choices for the first letter would be 26. The number of choices for the second letter, if we're talking about without replacement, without replacing that first letter back into the mix, is 25. So 26 times 25 would be 650. Now, with replacement, it's a somewhat different problem, but very similar. We have 26 choices for the first item, and then since we're replacing that first letter, we have 26 choices for the second letter as well. So 26 times 26, or 676. Consider this problem. Now all of these are very similar to one another, but they all illustrate a certain kind of nuance in this whole idea. And by the way, the idea of multiplying choices along the way is called the fundamental counting principle. And it is our basis for counting the possible outcomes in situations like this. Okay, here we're going to use the fundamental counting principle again. But in this situation, let's say we have 8 books. And we have a small bookshelf, and the bookshelf can only accommodate 3 books. And we'd like to know how many arrangements of 3 books are possible, choosing those 3 books from a group of 8 books. Now let's understand this, that if I chose book 4 and then book 6 and then book 8, let's say, and that's one arrangement. Another arrangement, though, could include this same group of 3 books. You see, I could have the arrangement of 6, 8, 4. You see, a different arrangement even though it included the same 3 books. That's kind of an important idea. The order notion then changes the arrangement here and therefore changes the number in the count of possibilities. All right, that's just a very important idea in this kind of problem. Okay, so once again, we're just multiplying the possibilities. And let's see, if we're choosing for the first book to put it onto the shelf, we're choosing from a group of 8, so we have 8 possibilities. Once we have chosen the first book, see, I'm just multiplying my choices here for the 3 books on the shelf. Once I've chosen the first book and put it onto the shelf, it's no longer available to be chosen. So for the second book, there are only 7 possibilities, and for the third book, there would be 6. And multiplying these, we would find that there are 336 possible arrangements of the 3 books on the shelf, taking them from 8 books. Now, this situation has a name. This notion about order being important and so forth, this is called a permutation. And in the notion of permutations, order is an important aspect in the calculation of a permutation. Now, the word arrange or arrangement is often used in this kind of problem. And there's even a formula that's associated with permutation. Now, I'm going to show you the formula here. It's written down here. But really, I kind of shy away from using it because the fundamental counting principle, that is multiplying the choices, works really well in situations involving permutation. But I want to show it to you just to contrast it with another problem that is similar to this. And you might notice that this looks a little bit familiar to a formula that we used in a previous section. Well, let's see. Now notice that the notation here, the permutation of 8 things taken 3 at a time, is 8 factorial over 8 minus 3 factorial, you see. And so we have, simplifying, let's see, 8 factorial is 8 times 7 times 6 times 5 factorial. I'm going to stop right there because I know that 8 minus 3 is 5 down here. So this is 5 factorial. So in the denominator I have 5 factorial, and all of those factors cancel with all of these. We have the 8 times 7 times 6 that we talked about earlier using the fundamental counting principle. Consider this problem. It says, in how many ways can the letters A, B, C, D be arranged? And this is a very typical permutation type of problem. We're just multiplying the choices for each of the letters. So we have 4 letters, and we multiply our choices. So we have 4 choices for the first letter, 3 for the second, 2 for the third, and only 1 choice for the fourth. Now this is the same as 4 factorial, but it turns out to be 24. Here's a variation on the same theme. How many 3-digit area codes are possible if the first digit cannot be 0? Now, you see, although on this problem we could have used the permutation formula, on this problem it really doesn't work very well. And the fundamental counting principle needs to apply here. Because although we have 3 digits for our area code, we have a restriction on the first digit. And when restrictions come in, a lot of times the formula just doesn't work. So let's see, how many 3-digit area codes are possible if the first digit cannot be 0? Now there are 10 digits, and if this digit can't be 0, then we only have 9 to choose from. So we have 9 choices here. Then for this next digit, we have all 10 digits to choose from, so we have 10 choices, and we're talking about the possibility of replacement here. So we have 10 choices for the third digit. 10 times 10, 100 times 9, we have 900 then possible area codes under this restriction. Let's return to the book problem for a moment. Let's suppose that we have these 8 books that we talked about earlier, and let's suppose that we have a bookshelf that can accommodate all of them. We can put all 8 books on the shelf. So it's no surprise then that if we're choosing from this group of 8 and we're listing our choices for each book on the shelf, we have 8 choices for the first book, 7 for the second, 6 for the third, and so on all the way down to 1. That's just 8 factorial, which is 40,320. Another way to calculate it is to use our permutation formula. Now, it's a kind of an unusual situation when we have 8 things taken 8 at a time. Let me just show you how the formula works here. It's the permutations of 8 things taken 8 at a time. So in the numerator, it's 8 factorial. In the denominator, it's 8 minus 8, or 0 factorial, which we know to be 1. So 8 factorial over 1 is 8 factorial, and we get the same result, of course, as we did